congratulations, everyone who made it so far. You have all done an amazing job, and we are very, very proud of what all you have done in the project phase. So we're really, really happy and really excited to see your presentations in a few minutes. Let me quickly start with an overview of the entire Womanium program, all the things we have done together, and a little bit of demographics on how many participants actually participated, how many projects we received. The judges had a hard time going through a lot of hundreds of projects, in fact, and getting to the finalists. It was a tough couple of days for all the judges involved. But yeah, let's get to that. Starting with Womanium. Womanium is a nonprofit organization based out of Washington, D.C., and it started about 7 years back. And since then, the entire goal of Womanium has been to create the scientific leaders of tomorrow, right? And try to advance women in STEM. With these core two pillars, we have been working on a lot of technologies. Quantum is just one part of it. But apart from that, on aging technologies, biomedical science, astrophysics, astrobiology, a lot of very exciting stuff. And if anyone of you is interested in learning more about that, you can always reach out to the Womanium team, and we'll be very happy to talk about it. Apart from that, Womanium has been now able to create an impact in over 120 countries, which is huge. And we are really motivated to expand even beyond this. So next year, we want to push these numbers to at least 150 countries or even beyond that. So let's target everything together. A couple of years back with Dr. Mario Slot, we started the first quantum program in 2022, where the entire aim was about quantum computing and entrepreneurship. An year back, we started with quantum computing, sensing, and communication. And this year, we took it another step forward and started working on real-world problems. And that is where QSL came into the picture. And all the projects you have been working on comes into the picture. So today, along with the awards, along with the grants, many of you will also get nominated for QSL fellowships, which is a very interesting part where you get to work on real-world problems with some of the best industry partners we have had. And you will be working alongside the best researchers. So stay tuned for that. I'll share more information about that in a minute. Yeah, so that was Womanium, and we have been very generously supported by a lot of partners. To name a few, the three key partners for our 2024 program have been the US Naval Nuclear Laboratory, Fraunhofer ITWM from Germany, and Classiq, a quantum computing company from Israel. We are very, very proud of all the partners listed over here, but many more as well who have been with us, continuously supporting our initiative, our goals for the past many years. Thank you, everyone. And with this, we come to 2024. Our Womanium Global Quantum and AI program, we started with the aim and with the goal of creating real-world applications. We wanted all the participants to learn skill sets and learn specific training skills which are relevant to the industry, right? So at least the ones who have done the projects in a good manner, I am pretty confident that you are in a good trajectory to land some pretty cool jobs in the quantum industry in the coming few months. All the participants who did successfully submit their projects and pass the passing criteria will receive project certificates. And these certificates are industry recognized. You can put them on your resumes, on your LinkedIn profiles, on your portfolios. So yeah, all the best for that. Many of the participants today, after the demo and after the presentations, will also receive certain Womanium grants. And these Womanium grants are focused on improving your quantum journey forward. So whatever you want to do, perhaps you want to create a YouTube channel, perhaps you want to publish a paper, there are certain monetary aspects required in each of these steps. And Womanium will be very generously supporting your journey throughout that process. And finally, the QSL fellowships. Very excited for that. And let me share a little bit more about this in a few minutes. But before that, we had over 4,300 participants registered in this summer program. This is by far the largest Quantum plus AI summer program hosted. And we are very proud of all the people who have joined us and learned something out of the entire program. Over 85 countries were represented, which is pretty successful on a global front. As I mentioned, we want to expand this even beyond. So next year, we'll be targeting even higher numbers. And with your continuous support, I'm very positive that we'll receive the results. We had over 44% female participation in the entire program. And this is, again, true to the entire motivation that Womanium wants to encourage more participation, more girls to participate, and become role models for new girls, for young female participants in the STEM fields. So we had a very consistent 44%. It would be nice if we can increase this percentage even further, but as a program, we are open to anyone and everyone who wants to join. Talking about the projects itself, we had 152 teams successfully submit the projects, which is huge because these projects, for the past 1 month, you have been working tirelessly. You have been working on different modules. So even after going through all the modules, all the lectures, you were able to successfully submit the projects. That in itself is a huge deal. So thank you everyone who successfully submitted the projects. Out of 152 teams, we had over 86 teams who successfully passed the passing criteria, and all the 86 teams will be receiving industry recognized participation certificate of achievements for the Womanium projects. So congratulations everyone who passed the projects. We will soon share the details of who all passed in the Discord server, and all the passing teams will also receive a mail from the Womanium team announcing their certificates and everything. This process might take a couple of days, so please stay tuned for that. And the finalists, the 29 teams today will be performing in front of us, presenting their solutions. Very, very excited for that. And very congratulations to all the participants who made it so far. Congratulations once again to all the finalists. You have done an amazing job, and this is the final step before you secure some amazing grants, awards. So all the best for your presentations. During the course of the entire project phase, we had over 46 countries submitting the projects, which is pretty cool in terms of diversity and demography and geography. But apart from that, I am also impressed that even after having this spread all across the globe, participants were able to communicate and collaborate across very large time zone differences as well. So I'm aware that many participants have been waking up at odd hours, working in odd hours, trying to communicate through text channels like Discord, or maybe hopping over Zoom and collaborating with your team members. It's amazing. It's truly an achievement which you all have received so far. And with this, we come to the demo day. So agenda for today, in a couple of minutes, we'll start the project presentations, followed by judges deliberating each of the projects. The award ceremonies will be held right at the end of the demo day, so please stay around for that. The award ceremony has 3 parts to it. We have the Womanium grants, we have the QSL fellowships from our partners, and we have some surprise awards which are there for everyone. They're not just only for the finalists. So even if you're not a finalist, stay tuned for the award ceremony. There might be something for you over there. And after that, we'll just stay around for some happy hour and celebrations with everyone. Now, how do you want to do the team presentations? There is a total pitch time allocated for every team. That is 3 minutes. We will be very strict on the 3 minutes. There would be timer popping up in each presentation. And as soon as the timer goes off, we will request that team to please stop presenting. This is just to ensure that all the teams get a fair amount of time presenting their solutions, their submissions. And please, please keep an eye on the timer and know when you want to stop. A couple of advices and suggestions. Please keep your slides ready for screen share. Please keep your mic and video to the best quality. You can already test that by exiting the meeting and doing a quick Zoom check so that you do not waste time during the presentation itself. And with that, I think we are ready to start with the presentations. The first one, we'll start with NNL. So a little bit about a partner. The US Naval Nuclear Lab is one of the best naval labs in the entire world. We have been working with them for the past year, and they have been very generously supporting our entire QSL initiative. For those of you who do not know about NNL, they were in fact the first organization to practically deploy a nuclear power reactor. Amazing, right? But they were also the first ones to develop a nuclear powered submarine, which is the USS Nautilus. A USS Enterprise, the first nuclear powered aircraft carrier, was also coming from NNL. And they also had the first commercial grid scale reactor. So a lot of first, and this kind of gives you a hint to the level of work and to the scale at which NNL is responsible for working in some cutting edge technologies. And we are very proud to have them as partners for this entire project phase, for the QSL fellowships, and they have generously supported this project. So this project was about quantum and AI for climate, with the entire goal of creating new solutions and brainstorming new ideas on where quantum technologies and machine learning, artificial intelligence can synergize together and try to come up with some good models which can help us solve the current climate problems. The goal over here was very open-ended, so all the teams were free to choose their own models and come up with their own presentations, but we are very impressed by the creativity all the teams have shown. We have our judge with us here today as well. Dr. Brian McDermott has been the key POC from the entire NNL team, and he's also the judge. He is responsible for judging, but is also responsible for a lot of other exciting work. He heads the quantum division at NNL. And if you get selected for the QSL fellowships, you will also get a chance to work very closely with Brian and his team, which is a very, very fantastic experience if you listen to my word. So yeah, enough of us, enough of our partners, and on to the presentations. So with this, I would like to invite the first team we have for our presentations today. Let me quickly stop sharing my screen. And the first team we have is Team Quercus. So How Mac and Amardeep Singh, please go ahead and present your screen.
Hey, thank you, everybody. When we think about the various different issues that tend to come up with being able to predict certain factors that we want for climatic models, there tends to be a bit of, you could say, asynchronicity that comes from either a lack of data or a lack of understanding from physical parameters, which is why the team had gone into this long process of using physics-informed neural networks to be able to make the actual, you could say, outputs and models much better than. We had gone through a long process of checking into various different equations and various different methods of involving those into existing quantum-based architectures to be able to better understand how we can better measure these things. Going forward ahead with that, parse through a lot of different papers again, looking at exactly how you could say quantum pin structures and architectures, how those could be incorporated with typical TensorFlow Keras or Qiskit-based, you could say, mainframes. And with that, we were able to at least get to a state where we had some initial methods that helped us better understand how we could look at different flows and different geometries for climactic models again. The data sets that we were dealing with were mostly involved onto, you could say, factors such as risks for flooding, elevations that could come from flooding in different regions, for example, or just even the movement of CO2 in different fluxes across different continents, for example. Because of the lack of physical data, again, this does get extremely complicated, but as we were able to incorporate the technology for pins in this particular example, it was made much faster and we were able to track these examples on a much greater scale again. These are, again, just some reflections from, you could say, existing papers that we were able to incorporate into what we have, basically combining items from the Navier-Stokes equations and Burgers equations to our existing parameters, and the results, so to speak, for themselves. We have current sort of models that do perfectly sort of capture onto physical media to a great extent. It's taken quite a long time to be able to like pass through different epochs to many of these items again. But the key idea is that using certain kinds of architectures and certain models for physical, you could say, constraints, we were able to make the system much better in sort of incorporating many of these elements. These graphs are just a representation of many of these individual, you could say, scraping of information from, you could say, land masses or just even looking at fluxes for different gases across continents. And we're able to match that quite well with, realistic conditions again.
Less than
This
10
isn't to
seconds.
say that pins are the best solution for all kinds of circumstances. This is just to say that using certain constraints and using certain architectures, we're able to get to that sort of an example again. Right now, the team is looking into involving, more direct actions and, adding other constraints which could make these models better. We are looking into more stochastic noise to be able to account for many other differences that would come with the system, so to speak. And
We
yeah,
could wrap
that's
up. That was
just.
our 3 minutes.
Would you like to conclude really quickly?
Oh, sorry, I was muted. No, that's all we have for the moment. No other conclusions.
Thank you.
Okay. Thanks a lot, Amardeep. And we move on to the next team, that is a Quantum Mission. Aylan Perez, Hugo Christian, Gilberto Sebastian, and Nidia Asaf. Please go ahead and share your screen.
All right, I need him to stop sharing for me to share. Okay, thank you very much. Hello, my name is Nidia Asaf, and I'm honored to present to you on behalf of our team Quantum Mission. This is the video that's going to kind of walk you through the South Atlantic anomaly, which is an area of interest for us because it represents a weakening in the Earth's magnetic field and an increased exposure on solar and cosmic rays. Very well, so let's dive into the details. This anomaly is not only expanding, it is moving. And in this area, the limited monitoring is due to the risk that it presents to the satellites when you can have a single event upset that could even destroy parts of the satellite. We are looking into climate impacts as it relates to climate change in this vulnerable area. And what we did was complement the swarming Copernicus constellations with local data from the Argentinian's weather station and have focused on an area of Cordoba and Santa Fe. The implication for us would be to see if this is a good area to research remediation strategy for warming impact. This is a visualization of the Copernicus satellite data. And as you can see, Argentina's UV solar index, which is impactful to our health, has reached an extreme risk level of maximum 5 minutes of exposure in certain areas. Our results were indeed that the area is warming at a faster rate, which is concerning. We have, after several models and computational limitations, arrived at a SARIMA, which is a seasonal ARIMA model, at a 95% confidence that the maximum temperature for 2024, which would be the summer of Argentina in December, would be a 42.5 degrees Celsius. Based on this, the rate of warming is significantly faster than the global climate change average, which would have predicted an increase of only 0.39. For every opportunity we saw, it was related to a challenge. Complementing low orbit monitoring with quantum sensors, given the low magnetic field interference, could yield higher fidelity. For the limitation on scope, we really want to entice people to look into additional research on water as it relates to food security. And given the anomaly is moving, consider a plug and play model that complements local data and even space weather data for alert systems that can help the individuals here for risk and precautions. Then lastly, just want to invite you to look at this area for remediation strategies on water, food security, drought. Here are our references, and thank you so much for your time.
Thank you, Nadia. Could you please stop sharing your screen and we move on to the third presentation, Quantum Maniacs, Aditya Sinha and Khadija Naz Sahwi.
Great job, Nadia.
Hi everyone, my name is Khadija Naz Sahwi. I'm here with my teammate Aditya Sinha. Our topic is on the effect of incorrect agricultural practices on climate change. All across the world, especially in a country like India, where the majority of the population resides in rural areas, agriculture is still a primary source of livelihood. However, due to widespread poverty, lack of education about appropriate farming measures, and lack of access to good quality resources, farmers are generally unaware of and resort to poor cropping methods, which renders the soil unusable after just a few years. Growing the wrong crops not suitable to the nutrient level of the soil or of the rainfall in the region leads to the soil losing all its nutritional value, which forces them to use chemical fertilizers, which in turn harms the food grown, the water table, the soil, basically everything. So what is the possible solution for this widespread problem? A crop yield prediction system that adapts with the changing patterns of rainfall and soil nutrition. How will that help our case? First, tailored crop recommendations based on soil data address nutrient deficiencies and optimize environmental conditions for crop growth. They ensure efficient use of fertilizers, water, among other resources, and hence contribute to sustainable practices. They also enhance crop resilience to climate variations, among other such benefits. In our solution architecture, we have used front end in Next.js and back end in Flask. We've connected the front end with the back end using REST APIs. The Flask back end has two machine learning models that expose two APIs. The model used for rainfall prediction is the random forest regressor model, which is an ensemble learning model that combines multiple decision trees to predict continuous outcomes, averaging their predictions to improve accuracy and reduce overfitting. The model used for crop prediction is a type of deep learning model where information moves in one direction through layers of neurons from input to output with no cycles, making it ideal for tasks like classification and regression. The success of our model can be seen from the following graphs. The random forest regressor appears to perform reasonably well for rainfall prediction. It captures the general trend, but struggles with extreme events only. Here, the red dashed line represents the ideal prediction, and the blue dots represent the individual predictions. Most points cluster around the red line, indicating that the model's predictions are generally good. On the right, the histogram shows the distribution of prediction errors. The histogram is centered close to 0, which is good. That is, the majority of errors fall within a relatively small range around 0. For the second crop prediction model, the model appears very effective for crop yield production with high accuracy and good generalization capacities. In the left, the graph in the blue shows the training accuracy, and in the orange shows the validation accuracy. And the model achieves and maintains over 95% accuracy on both sets. The graph on the right displays the training loss in blue and validation loss in orange. The loss decreases significantly and stabilizes at a low level for both sets. The future scope is that since several countries already have free testing labs, such as in India, we can have a tie-up with these existing labs, either government or private, and expand this further. So thank you, and these are the references.
Thank you. Wonderful, Khadija. And we move on to the next presentation, that is Quantum Minds. Quantum Minds. Saif, Rehab,
Okay.
Elkadi. Yeah, please go ahead.
Okay, hello everyone. Today you are addressing a critical issue in the fight against climate change, methane emissions. While we often hear about CO2, actually methane has a bigger impact on global warming. It has a global warming potential 28 times higher than CO2. The problem is methane emissions are still growing. Our focus is on detecting methane leaks, which is essential for slowing down this rise. So as you can see here, the energy sector, particularly oil and gas industries, is a major source of methane leaks. To tackle this, we use Sentinel-2 satellite images from 3 major oil and gas producing countries, Algeria, the US, and Turkmenistan. We reviewed the existing works on methane detection. The UNET model was widely used. However, there are still gaps that need to be filled, such as a lot of false positives in their results. Our proposal is a hybrid quantum classical UNET model. In this approach, we propose to replace traditional convolutional layers with quantum convolution layers in 3 key parts: the input convolution, down, and bottleneck blocks of the UNET model, of course. We use 2 types of quantum convolutions, Quanf 2x2 and Quanf 3x3. The QCNN model starts with data encoding. We used angle encoding, and we tested with multiple ansatz. In our experiments, we implemented our models using PyTorch and PennyLane. We tested different configurations by incorporating QCNN in these blocks, like using QCNN in just one block or across all the 3 blocks. For example, in the architecture 3, we used QCNN only in the bottleneck block, and in the architecture 5, the QCNN was in the 3 blocks, like you can see here, true, true, true. So is Quanto better than classical? Our results showed that the architecture 5 had the best performance, but due to limited computational time, it was only trained for 2 epochs. So we selected the architecture 3 as the best model, which still outperformed the classical unit. And yes, here are our metrics for the best model with 96% of accuracy. And as you can see here, we also developed an application to present our findings. You can see the interfaces here. In the future, we plan to expand our dataset and add more data sources like Sentinel-5P. Technically, we will experiment with new quantum circuit designs and more epochs, test real quantum devices, and optimizations of the model. Additionally, we aim to commercialize our solution by developing a platform for methane monitoring across oil and gas industries. And thank you very much.
Amazing. Thanks a lot, Radia. And we move on to the next presentation, that is Q-Earth by Mahmoud El-Kharji.
Yes. Hello, everyone. I'm Mahmoud El-Kharji. I will be presenting the Q-Earth project. Accurate daily temperature prediction impacts various industries. For example, a study by the International Energy Agency found that accurate temperature forecasting can reduce energy consumption by 10%. The problem with the current weather forecasting method is that they struggle to compare complex patterns in large data set. They are also slow to adapt to new trends and changes in data. When we talk about complex pattern in large data sets, it is where the power of machine learning shines. In 2022, a study by the European Center for Medium Range Weather Forecast found that the machine learning models improve forecast accuracy by 20% compared to the traditional methods. In order to solve this real-world problem, we have to use a real data set. The daily temperature data sets contain an average temperature for 125 countries from 1995 to 2022, totaling in 2.9 million entries. First of all, we conducted pre-processing and analysis steps to understand our data. Then we split our data into training, test, and validation sets. After analyzing the data, we identified it as a regression problem. Using this model, we can predict the temperature of any country or region at any given time. We started with a baseline model using LSTM. The reason for the choice was based on a paper called Prediction of Temperature of Major Cities in India. They worked with the same data set and applied LSTM. So we did the same and marked it as our baseline model. We achieved a slightly better results than the reference study, thanks to our data engineering and pre-processing steps. The second approach was SVM. It's known for its efficiency in regression problem. As we see, we outperformed LSTM in some matrices. Then we added the quantum algorithm. QSVR can process large data sets and perform complex computational more efficient than the classical one. We benchmarked our model across multiple IBM quantum hardwares, and the results were better. Our model will be offered as an API that will provide long-term, real-time, location-specific weather predictions, enable integration with websites and mobile devices. During our work, we faced several challenges that we plan to overcome. The first one is restricted time quota for quantum and GPU hardware, which limited our ability to learn large datasets and complex models. Also, working alone made it difficult to conduct in-depth experience and extensive model tuning. We plan to extend our model to predict other variables like CO2 and methane emission. Also, conduct a market analysis to create a business model canvas and develop a subscription-based API platform for various industries. Addressing these challenges will enhance community insights and facilitate integrating quantum computing into various algorithms. That was our solution in a brief. Thank you for, you can find more technical details in our GitHub repo, and please do not hesitate to ask any question. Thank you.
Great job.
Thank you. Yeah, thanks a lot, Mohammed. Next up, we have QAI Climate MX by Carlos Arauz Alvarado.
Yes. Hello, everyone. I aim to present a solution for the Poisson equation using the HHL algorithm. The Poisson equation is a fundamental partial differential equation that describes potential distribution in static fields. Solving the Poisson equation efficiently is computationally challenging. That's why I aim to present here a quantum computing solution to solve this equation efficiently. This equation plays a crucial role in modeling various phenomena. For example, it is used in groundwater flow, since it is essential for understanding aquifer behavior and managing water resources. It is also useful in atmospheric science, since it models electrostatic potentials, aiding in understanding in weather patterns. Traditional methods require heavy computational resources and face exponential complexity with larger problems. That's why I aim to apply the HHL algorithm to solve this equation exponentially faster, because it has potential to solve systems of linear equations exponentially faster than classical methods under certain conditions. Remembering that the Poisson equation is a partial differential equation that has this form, where we have the Laplacian operator, the potential function, and a source term, I rewrite this problem into a matrix equation of the form Ax equals B. Then I design and implement a quantum circuit using Qiskit, where the quantum state corresponding to the vector B is initialized. Then controlled unitary operations are performed based on the matrix A. Then I perform quantum phase estimation and I measure the results. The quantum circuit is then simulated in IR simulator, where a noise model is incorporated to reflect realistic quantum errors. The output is visualized using a histogram, and we have here the results. The ancillary qubit was measured in state 0 approximately 75% of the shots, And this demonstrates that a correct solution was made because quantum operators, such as phase estimation and conditional rotations, were applied successfully. This demonstrates that the HHL algorithm's potential in quantum computing for solving the Poisson equation, advancing its applications in science and engineering. The next steps correspond to implement advanced error mitigation techniques to reduce noise model impact and improve results accuracy. Also to explore the scalability of the algorithm by increasing the number of qubits to handle larger and more complex problems. And the current quantum hardware faces significant challenges, such as including limited qubit coherence time and high error rates, which hinder scaling and achieving more accurate results. And that's all. Thank you for your time.
Very interesting. Thanks a lot, Carlos. And we move on to the next presentation that is by Q Mars, Rishikesh, Abdullah, Sarah, and Mehem.
Yeah, so our presentation focuses on using classical and quantum computing methods for seismic data analysis. Seismic data is generally important for understanding the subsurface of the Earth. It's usually very high dimensional data. There's a lot of noise issues. There are a lot of very complex patterns, which is where quantum computing can come into use. Now, classical machine learning methods have been used before. So we sort of explore quantum methods a little more. So the methods that we used include artificial neural networks, autoencoders, quantum versions of each of those, quantum kernel PCAs, and quantum phase estimations. So the classical neural network and classical autoencoder architectures are sort of laid out in front of you. The quantum methods use different gates or different circuit setups to sort of process the data better. So when we compare between each of the models that we had, the classical methods did seem to perform fairly well. The quantum methods, however, did not lag far behind. So our quantum autoencoder has an error of 0.003, a mean squared error, which for values between 0 and 1 for the data is fairly good. So we can see over here that when we use the classical autoencoder, for example, for trace reconstruction, which is useful for denoising the data or reducing the dimensionality of the data, for the classical method, we do reconstruct the trace pretty well, but the quantum method is actually also very capable of reconstructing the trace. Quantum phase estimation is also able to sort of understand the structure of the data very well too. So some of our success metrics include that we were able to improve the trace reconstruction metric. So our mean squared error was originally around 0.2, it dropped to 0.003. We were able to reduce the dimensionality. One of our very important results is that we did not see that quantum phase estimation was used before for this. So we were able to implement an algorithm for estimating the seismic-related phases. In the future, we would like to extend this to larger data sets and use more complicated or better structured architectures to get slightly better results for some of the other models that we use. And we would like to investigate other techniques and algorithms for this as well. We were obviously limited by computational resources, and we may need to refine our models a little more. That is it. Thank you very much, and have a good day or night.
Great job.
Thank you, ma'am. Wonderful. And with this, we are almost halfway through the NNL presentations. And then I would like to welcome the 8th team we have, Entangled Engineers. Please welcome Amit, Karan, Sayam, and Shreya.
Hello, judges. So is my screen visible?
Yes.
Yes.
Yeah. So hello, judges. I'm Karan and we are team Entangled Engineers. I hope you all are doing pretty great today. So my team members include Shreya, Amit, Sayam, and myself. So the problem statement that we have chosen for ourselves is rising global is water portability. So according to the Quantum plus AI climate theme, we thought that this would be pretty suitable enough for us to solve the natural issues. So due to the rising global temperatures, it would lead to several other natural calamities like droughts and floods, impacting water availability and its quality. So the major challenge that we'll be solving over here is predicting water potability in changing environmental conditions using several AI models and quantum techniques. So the data sets that we have drawn from includes various chemical properties like pH, hardness, solids, and other chemical properties of water that would define its quality, which would conclude in its suitability for consumption and for other uses. So at the beginning, we have utilized several AI models like light GBM, bagging classifier, XGBoost, and gradient classifiers in passing it individually and integrating these individual AI models, comparing the results on separately by integrating this with quantum models and quantum algorithms. So the quantum algorithm that we will be utilizing here is QAOA, which is one of the most powerful optimization models, which will be integrating with the individual AI models. We'll be generating a confusion matrix and similarity matrix by defining several hyperparameters with the QAOA algorithm, and will then be passing it through the QSVMs for further classification. These are the metrics and the results that we have generated alongside by this is the combined results of both quantum plus AI. The quantum approximation and optimization algorithm is the similar algorithm that has been implemented alongside all of the different AI models like light GBM, gradient, and bagging classifiers. And we here have the similarity matrix that we have generated alongside. So now this is something very interesting that would be looking forward to as the future scope and implementations that we have planned for. So we'll be integrating the quantum AI models with the several advanced quantum algorithms in real-time implementations with the quantum processors like Osprey and quantum systems. We would like to bring in the quantum AI memristors into use for the intelligent optimization for storage capabilities. On the software end, we plan on extending the quantum AI model with the quantum annealing using D-Wave Systems Ocean SDK. We would like to bring in the Shor's algorithm for the multimodal frame for the water potability properties and sync it to a neural regression. We plan on manipulation of the IC chips into the neural chips for intelligent selection of data modules. This would enable us to extend our capabilities not just for the water challenges, but also to the other natural resources like air and gases and solve major climate issues. Thank you, folks.
Thank you. Wonderful. Next up, we have Entangled Energy. So please welcome Mohammad Al Mahdi Abdullah, Suhail Mirza Soli, Maria, and Pooja Chakraborty.
Hi everyone, I'm Maria and I'm representing my team Entangled Energy. My teammates are Sohail, Mohammed, and Pooja, and our project is on optimizing materials discovery for photovoltaics in space. PVs are a rapidly growing renewable energy resource that converts sunlight into electricity. They have many applications in space, from powering the ISS to future projects like solar-powered data centers and power plants. The space environment presents many challenges like debris, reactive oxygen in atmosphere, and solar radiation that can affect the PV's performance. So space PVs are designed differently from ones here on Earth. Here is an example of one, and for our project, we specifically focus on finding materials for the PV cell that can help with reducing the effects of solar radiation. So now the problem is that there are so many materials to choose from, and running the experiments to find the best candidate is very expensive. For our solution, we want to narrow down the search space for potential best candidates. We start with a database of materials and pass it to a binary classifier that tells us whether a material is potentially suitable or not. From this list, we pass it to a quantum method called DFT and EDMFT that predicts the material's dynamic properties to calculate a value called displacement threshold energy. And this value is needed to calculate the non-ionizing energy loss values. And then lastly, we input these values into a simulator that tells us the end-of-life performance of a PV material over a given period of time. And at the end, we would then have a smaller pool of candidates for PVs in space. Now I'll walk you through some of our results. So we trained a binary classifier that assigns a 1 to potential materials and 0 otherwise. And our data set, it performed well on our test data set and predicted a high number of true negatives and true positives, and we got an accuracy of 98%. Moving forward, we would like to train our binary classifier on less features and consider other factors that affect a PB's performance. We would also like to create a pipeline for the entire process and a request for quantum credits for our quantum method. And lastly, we would like to validate our results with actual experiments to measure the overall performance and compare it to other methods. Thank you all for your attention, and for more information, please feel free to scan the QR code.
Thank you. Very good, Mariam. And next up, we have eco-cubators. Maral, Shrija, Muhammad Bakar, please go ahead.
Hello, my name is Shrija Das, and I'm representing our team of Maral Mahmoudi Kamlabad and Muhammad Wakarami. And our project is on real-time climate temporal series anomaly detection using quantum machine learning compared to classical machine learning. These are natural disasters in India in 2024 alone, which is devastating for daily life, economy, and infrastructure. Our project, however, successfully picks up on anomalies in these regions, potentially allowing for early detection and many lives to be saved. Here's how we did it. We started with satellite data from Copernicus, and we chose to focus on one geolocation, India, during 2024. Through data visualization, we were able to take advantage of the many features such as surface pressure, sea levels, and vegetation. This rich data allowed us to train two models, classical and hybrid quantum. Both models required the same preprocessing and data reduction steps through principal component analysis, PCA. We made use of the isolation forest algorithm for classical machine learning. But let's go into more depth with our hybrid quantum model. So we configured quantum devices for quantum phase estimation, QPE, and Harrow-Hassidim-Lloyd HHL algorithms. We fine-tuned the HHL circuit with operations such as Hadamard and CNOT. We also used random parametrized quantum circuits and identified anomalies by comparing results to a 95th percentile threshold. Now, beyond the quantum model performing 11 times faster and with a greater accuracy than our classical model, what's even more exciting is that our predictions coincide perfectly with actual events. For example, according to CNN, there has been many glacier bursts, flash floods, and landslides near the Himalayan region, which is visible in red circles for both of our models. We also picked up on the heavy flooding that was going on in South India, shown in the green squares for both models, and storms in the Tibet region, which is highlighted in yellow circles. Both events were highlighted and broadcasted by Reuters and New York Times. Another interesting observation is the anomaly detected in the Arabian Sea, which is shown with a yellow arrow for a quantum model. This is interesting since Pakistan had declared this as a no-fly zone for missile launching on May 14th to 15th. Similarly, Yemen's Houthi says that they targeted MSC Saravi vessel in the Arabian Sea. These findings are backed also by recent articles from PV magazine stating the detection of mixed irradiance during extreme weather around the Arabian Sea. This goes to show the impact of warfare on our oceans and climate, creating a potential hotspot. Some future plans include using real-time weather data for instant threat detection and expanding the study to even more geolocations. We also see commercial value in this, such as determining risky regions for building up infrastructure, like hotels, to prevent flooding and natural disasters like in Kalam. Some challenges include overcoming hardware difficulties and working with even larger data and computation time. All in all, thank you for listening. If you're as excited about the future of quantum AI and hardware as we are, don't miss the chance to be part of this groundbreaking journey. Reach out to our group member, Maral, at the email ID that is provided. Thank you so much.
Perfect. Thanks a lot, Shrija. And next up, we have confused QPALs. George, Sahani, Omar, and Shrikaran, please go ahead.
Hi there. My name is Siri, and I'm a representative of Confused QPALs. Our group project focuses on comparison of tornado damage prediction and accuracy between classical and hybrid quantum classical neural networks. The motivation for this project is the need for tornado damage prediction, as tornadoes are one of the deadliest yet common natural disasters worldwide. Research into tornado predictions has steadily advanced over the years, with machine learning being one of the most promising models, with 2 examples shown here. However, machine learning fell short in processing big and complex data, such as the Earth's atmosphere. To enhance its prediction accuracy, quantum properties can be implemented into the models. Based on our research, quantum properties should allow better data process and analysis for complex climate dynamics and reduce computational costs. Thus, our goal is to investigate how quantum properties such as superposition and entanglement can benefit machine learning prediction for tornado damages. So our implementations are as follows. We first prepare our data by pre-processing and encoding, then input our data into our multi-output classical neural network model that we had created and run the model. We then convert a quantum circuit into a quantum layer, then implement it into our neural network, then run the modified model. Finally, we compare both models to see if the implementation of the quantum layer increases its accuracy. So here's our data set. Here are our inputs, and here are the outputs that we are expecting, with the criteria for classification of property loss right here. Here's the architecture of our models. Above are the layers of the classical and the hybrid model, respectively, with the structure details on the bottom left. On the bottom right, we have the quantum circuits used for the quantum layer. The quantum circuit encodes features into qubit rotation using the RX gate, followed by single qubit rotations and a loop of CNOT gates that entangle neighboring qubits. This simulates interconnected neurons through quantum entanglement. And here are our preliminary results. Based on our mean average error analysis for the first 3 here and the accuracy comparison for the bottom right, we can see that the classical neural networks outperforms hybrid models for predicting the number of states and the fatalities. However, hybrid models perform better in predicting the number of injuries and property loss. Based on our preliminary results, we then conclude that while hybrid neural network does have an advantage in predicting some variables, it does not show superiority in all categories. And finally, we hope to implement GPS satellite images as input to complement our current variables in the future. Thank you.
Thank you, Siri. Wonderful. And next
I
up
love
we
the
have...
photo.
Right.
Thank you.
Next up we have siblings, quantum circles, Maria, Daniela, Gilberto, and Fernando Torres. Please go ahead.
Yes. Hello, everyone. My name is Fernando Torres, and I'll be presenting our project of hurricane prediction using physics-informed quantum neural networks on behalf of my team, Sapiens Quantum Circuit. And without further ado, let's dive in. Hurricanes pose a significant threat around the globe, and it is a problem as old as civilization. I remember my grandparents telling me how their parents used a wooden stick to try to predict hurricanes. Here I am, presenting how quantum machine learning may be a better option for it. But this is not a trivial problem. Methods such as supercomputers, machine learning, and physical-informed neural networks have been explored for forecasting. To us, it seems like a natural next step to use physical-informed quantum neural networks. So we implemented a framework using a variational quantum circuit and a physical-informed neural network using PennyLane and PyTorch. For this, we used a serial feature map with trainable parameters to enhance information preservation in the Hilbert space, and added a series of ad-set layers that acts as the neural network. The predictions were made through the expectation value of a cost operator, and the parameters were updated using a classical optimizer. This optimizer responds to a loss function that includes both the data loss and the physical loss, using a gamma hyperparameter to control the effect on each one. The physical components have the Navier-Stokes and continuity equation for incompressible fluids and the Coriolis effect residuals. We encountered that we were computationally limited, so the results that we're showing only show the principle of action of the model. First, without any physical influence, that is gamma equals to 0, we trained for 200 epochs, and this resulted in the circuit learning the overall patterns of intensity of the original values, but without being able to predict outside the training set. Then, adding a little bit of physics with a gamma of 0.05, we trained for 100 epochs, and in this result, the model was able to predict better outside the training set, but sacrificing accuracy for fitting the data. Nevertheless, for high-intensity wind velocities, we had a higher absolute error. In conclusion, we achieved satisfactory result with just a few epochs of training, contrasting with the 200,000 epochs typically required for a conventional neural network. We found out that adding too much physics can lead to trivial solutions, and we would need to add an additional loss term. To further improve the model, we would need to include more qubits or use a more complex ansatz structure. This opens an avenue for future research to refine the use of physically informed quantum neural networks. That's it. Thank you very much.
Awesome. Thanks a lot, Fernando. And with that, we are almost at the end of the presentations. We have the final group with us, Team Blue. They were unfortunately not able to be here in person today, so they have shared a presentation, and I would kindly request my colleague Jasmine to share that presentation with all of us.
Hello, Womanium team. Today I'll be talking about how the climate modeling challenge addresses the need for accurate and efficient climate models that can run on standard hardware. Traditional models require extensive computational resources, limiting accessibility for many users. Our project aims to create an AI-based climate model enabling individuals and organizations to simulate Earth's climate effectively using historical data while ensuring fast performance on standard laptops or PCs. To tackle this challenge, we set clear objectives, such as data preparation. We collected and cleaned historical climate data and published simulation outputs, normalizing it and splitting it into training and testing sets. Model development. We designed and trained a neural network model that combines convolutional neural networks, CNN to abbreviate, to capture spatial patterns and long-term and long-short-term memory, LSTM, layers to account for temporal dependencies in the climate data. Demo application. We developed a lightweight demo application showcasing our model capabilities, which eventually provides quick predictions of temperature anomalies. The implementation was carried out in Python using TensorFlow and Keras, focusing on optimizing the model for standard hardware. As a result, the AI model completed training in just 30 minutes, generating predictions in under a second. These are the graphs that shows our results. We achieved remarkable results through our project, with a mean square error of 0.003 on test data. Our model demonstrated high accuracy, confirming its reliability in forecasting climate anomalies. Furthermore, this week training and prediction time showcase that complex climate models could indeed run on standard laptops. This project contributes to the broader field of computational sciences, including quantum science, by demonstrating the feasibility of efficient climate modeling on accessible hardware. Looking ahead, we recommend several steps to extend our project. Expand model coverage. Increase geographic regions covered by our model. Also, enhance model accuracy, integrate additional data sources and refine the model architecture to improve forecast. In addition, real-time simulation. Develop functionalities for real-time climate simulations. However, we face limitations such as current hardware constraints that hinder scaling to global simulations and challenges in accessing high-resolution real-time climate data, which must be addressed to fully realize these recommendations. Thank you.
Next up, we'll start with the Fraunhofer projects. So a little bit of background about what Fraunhofer is and what they do. So Fraunhofer in general is one of the largest research organizations there are in the world. In fact, one of the largest applied research institute in the whole of Europe. They have more than 76 institutes globally, so not just in Germany, not just in Europe, but the entire globe. And Fraunhofer ITWM, the one which we have partnered with and very proud of our partnership, they are one of the world's largest mathematical research institutes, and they work on software simulations, mathematical models, and many interesting things. A couple of highlights about Fraunhofer. So those of you who do not know about the organizations, they are the ones who actually invented airbags. Airbags which we all use in our cars, in our vehicles, from small vehicles to vehicles as large as aircrafts. Airbags are used everywhere for security purposes, and these airbags were invented at Fraunhofer. MP3 format, right? Even today we use this format for all of our audio files. MP3 was first invented at Fraunhofer. And finally, white LED. So all of the people who are using LEDs at their home, the white colored LED, which we all use, was first invented at Fraunhofer. So amazing institute, amazing research, and amazing inventions. And very proudly, they have partnered with us to create a challenge and a project called the Quantum Machine Learning for Conspicuity Detection, where the goal was to try to challenge the participants to come up with unique solutions and unique algorithmic developments in the quantum machine learning phase, where they can try to detect and do image classification models and try to improve how defects are detected in different machine lines in different operations within the industry. So the team size over here was maximum 2 people, and we received the highest number of submissions in this particular project. Very exciting to, I'm really excited to see all the projects start right now. So with that, let me welcome the first team to present. The first team is the Curies, Juliana and Manuela Profer. Please go ahead and share your screen.
Thank you very much. Hi, everyone. My name is Juliana, and I'm sharing the screen. Good. Welcome to the Curies speech about QML for conspicuity detection. Our team name is the Curies, named after Marie Curie. Here is the outline of the presentation. We are Manuela Profer and Juliana Sidimoro, both researchers in a not-for-profit research organization. The main goals of the project are resumed in this slide, mainly to accelerate effective path detection by means of hybrid quantum computing. The motivation of this study stems from the fact that classical methods are considered time-consuming in the learning phase. Our aim is to contribute to QC algorithm benchmarking as well. Let's illustrate our solution in 5 steps. In task 1, we developed familiarity with pennyling in basic and more advanced workflow. Task 2 and 3 were devoted to variational classifiers and convolutional neural networks. All steps for the first 3 tasks are thoroughly commented on. Speaking of learning the same function in task 4, we followed the approach suggested in a reference-friendly tutorial to exploit quantum dropout and avoid overfitting. Finally, in task 5, we implemented a QML model intended to detect a defective production by using a real dataset from industry. Our metrics of success are related to what we have learned so far. Specifically, in task 5, we learned the processing technique of image data to create a small data set. For conspicuity detection, we ran a convolutional neural network workflow using 4 and 9 qubits. And we've got that 2 times 2 tensor convolution results were better. We carried out a tentative implementation of variational classifier, fixing the curves or narrowing down the feature map to fit a quantum surface. Some partial results are enclosed. Anyways, that was a valuable opportunity to approach QC and QML. We enjoyed the efficient learning while performing the whole program's assignments. We treasure what the Womanium quantum program offers us, and we started exploring the broad field of application of quantum computing for AI. We are motivated to delve into more methods and more ideas. For instance, transfer learning, a wavelet transform plus quantum layer, quantum PCA, etc. We would like to build a workflow for unsupervised learning on this data set. And specifically, we are interested to see what methods can scale above the 10 qubits limit. And we did have a lot of fun during the project, so we'll carry on. Thank you all, and greetings from the Curies.
Wonderful. Thanks a lot, Juliana. Well within the
Thank you.
time, and I'm glad you had fun.
And she also has
next,
2 Marie Curies. Yeah, 2 of them.
Yes.
Right. The next team we have is the detection duo. Please welcome Martina and Hussein.
Yeah, do you see my screen?
Yes.
Yeah, thank you. Hello, everyone. I'm pleased to present our project. Let me introduce myself. First of all, I'm Martina Truba. I'm full stack developer, and my teammate and Hussein Shiri, I'm an engineer in there. The project was divided into 5 tasks. All details regarding this task are available in the report file on our GitHub. Today we will focus on the last two tasks, 4 and 5. For task 4, we start with classical model using simple neural network. We then implemented a quantum model depicted in the center, which includes an encoding and training block. Remarkably, it took only 30 epochs to train our quantum model sufficiently. Through our experiments, we observed that the model required only 4 data points to effectively learn the sine function. Subsequently, we extend the problem to learning a function with larger frequency spectrum. We implemented a model based on the work of Maria Schultz, as shown here. For this spectrum, we had to use 5 layers. The model performed well, as you can see from the comparison plot on the right. For task 5, first, we started by pre-processing the images through, for example, cropping and resizing. Then we applied Mann-Schüttel reduction using PCA and autoencoder. For the core model, we implemented a quantum tensor neural network using both 4 and 8 qubits. We experimented with different loss functions. And finally, we calculated performance metrics to evaluate the effectiveness of each approach. As part of the second hour approach, we use a quantum neural network with a mirror architecture. The table shows our results with different loss function. The exponential loss function gave us the best validation accuracy at 92% and test accuracy at 89%. Challenges and future scope. One of the key challenges was the need for substantial computational resources and handling large image dimensions. We also focus on implementing a novel approach while emphasizing the creation of maintainable and reusable code, which is designed to be extended. Looking ahead, we plan to compare our model with others, expand it for multi-classification and testing on the hardware. Additionally, we want to explore new approaches, such as detecting anomalies by analyzing frequency pattern in images. Thank you. And all details are available in GitHub repository. Don't hesitate to ask any question.
Amazing. Thanks a lot, Martina. Next up, we have Team Tushar Nadeen with Tushar Pandey and Nadeen Matanda Muela.
I'm presenting QMN for conspiracy detection and production. The problem statement of this project is that detection of wear defects in TIG rating is still a critical problem for automotive and aerospace industries. For that reason, we developed a quantum machine learning approach to process image data for classification tasks on a subset of the given data set and to outperform the current results of a scientific paper where they use the same data set, but a classical approach. Our model is a convolutional neural networks with trainable parameters and using angle bending as our base model. We also use performance matrices to perform the performance of our model and to compare the results from the paper. We classify our model on 2 and 4 classes. We also use different encoding techniques and different quantum layers to show the changes of our base model. The results on the base model using a 2-class and 4 classification model showed an improvement of accuracy comparable to the base model of the paper. This can be also shown when we output the performance matrices on the 2-class classification and also on the multi-classification results, where the accuracy was 98.5 and also an RC result of 100% was received. When we compared different encoding methods for example, IQP versus angle bending, we showed that angle bending slightly outperformed the IQP bending using the multi-class classification model. This was also the same for when we visualize our model, we show and see that angle bending slightly outperformed the IQP bending. After that, we used two classes to see if there was a difference. There was not a difference. Angle bending still outperformed the IQP bending. As a conclusion, hybrid quantum model demonstrates a superior performance in defect classification comparable to the scientific paper where they use classical approaches. And when we compared different embedding techniques, we saw that for our model, angle bending seemed to perform slightly better than IQP bending. We also used different quantum layers between the classical layers, and that also improved the accuracy of our model. For our future work, we would like to explore different encoding methods, and we would like to investigate faster convergence techniques for our classification matrices. And for that, we would also like to publish our findings on the effect of encoding image classification tags, and also show that quantum machine learning models don't require that much data set. Thank you for your attention.
Thank you. Wonderful, Nadine. And next up, we have Team Penguin. And we have Kazuki with us here today to present. Please go ahead.
Okay, hello, my name is Kazuki Tsuoka, and during the Womanium Quantum Hackathon, I worked on conspicuity detection using a classical to quantum transfer learning. So in this project, I developed a quantum classical hybrid machine learning model to determine whether the wording has been performed correctly. The given dataset contains about 13,000 images of wording processes, and the goal is to create a model that accurately determines whether the welding was successful. In classical to quantum transfer learning, images are first input into a pre-trained model, and the output is then fed into a variational quantum circuit to predict whether the welding was successful. I used Resonate 18 as the pre-trained model, and the model architecture is as follows. So the images were downsampled to be compatible with the Resonate input, and the normalization and data augmentation are performed to improve accuracy. And next, the images are input to the Resonate, and the resulting numerical values are rescaled using a hyperbolic tangent function before being passed through angle embedding and input to the variational quantum circuit. And finally, the quantum circuit is measured, and the measurement results were further processed to determine whether the image is classified as a good weld or defective. As a result, the test accuracy reached a maximum of 95.4%. And the original paper reported a maximum test accuracy of 95.6% among all the models. So higher accuracy was achieved than most convolutional neural networks presented in the original paper. And finally, I would like to discuss the future scope. The quantum circuit I used this time was a small circuit with only 4 qubits. And to fully leverage the strength of quantum computing, more qubits are needed. However, the model I created with more than 4 qubits often led to overfitting. And exploring methods to increase the number of qubits while preventing overfitting might reveal the true strengths of quantum classical hybrid transfer learning. And finally, thank you for your attention.
Thank you, Kazuki. Wonderful. And we have the next presentation after that, that is Quantum Beams, Ricardo Riodo Santiago and Jose Antonio.
Good morning. I'm trying to share my screen. Sorry. So I'm having, I don't know why this got.
Desmond, can you pull up his presentation?
Yes, let me try to get it.
will present Antonio. Are you there?
I have the video of it, but there weren't the slides.
Oh, perfect. Well, we see it now. Go ahead. No, you had it. Please go ahead. We are losing time here as well. Can you change slides and test? Otherwise, we can put you to the end. Yep, it's working. Go ahead. You can start talking.
I think I will present. Okay, so yeah, okay, my name is Ricardo Santiago, and we are working on.
I will take the voice right now. Well, today we're going to talk about our project of the task 5 of Fraunhofer project. This project was developed by me, José Antonio Contreras Ortiz, and Ricardo Herrera Sanchez. The objectives that we have with this project was first to pre-process and prepare the dataset for the binary classification task, also to design and implement an hybrid and classical machine learning models, then evaluate both models and compare its performance, and finally integrate the model into Hugging Face platform so we can make it easily accessible for anyone to use. Next slide, please. For completing these objectives, first we designed two little scripts to reorganize the dataset first and then create a binary dataset. For this, we use 14,000 images for the training and 6,000 images for the validation. Next slide, please. The model that we designed is pretty simple. We use a vision transformer, a bait vision transformer, which is available in the Hugging Face platform. This transformer is delivered to us a vector of around 700 entries, which are fed into a dense layer, which simplifies the amount of labels that we have in our model or the problem that we are trying to solve. And this amount of labels also it's fed into this vector is now fed in the quantum circuit, which also it's configured to the amount of labels that we have in our problem. In this case, it's a binary classification problem, so we have a two-qubit circuit, which acts in kind of like a softmax function. And finally, we get the prediction. Here's the little circuit that we use. It's just the angle embeddings, which is just encoding of the information. And then we use a basic entanglement layers. Next slide, please. We have both trainings of both models. As you can see, this training was done in 5 epochs, and the accuracy was calculated on the validation dataset. As we can see, we have a pretty decent generalization for both models. Next slide, please. And finally, we have the comparison between both models. We use 30,000 images for the final comparison. As we can see, both accuracy, recall precision F1 and ROC are pretty high for both models. And obviously the classical model outperformed for a little the hybrid model. Next slide, please. Here's another comparison just using a confusion matrix. As we can see, the hybrid model has more misclassifications, but in general, it's pretty good also. Next slide, please. For the uploading to Hugging Face, we didn't manage to upload the hybrid model. We wanted to do like the classical one. He's just 2 lines to do a inference, but we didn't manage to do it. Next slide. And finally, for the feature scope, we wanted to integrate it fully with Hugging Face. We integrate more models, and maybe in the future we could have a section of Hugging Face so we can share our models. Next slide, please. Thanks for your time, and sorry for the inconvenience.
Thank you. Wonderful, Jose. And we move for the next presentation, that is Quantomics. How Mackie and Mohammad Reza Khadajo. Can you please unmute yourself? You're not audible.
Okay, let's go with this. 1, 2, 3. Hello, everyone. We are Team Quantomics, Mohammed and Haumak Yang. Our project is quantum machine learning for conspicuity detection in production. Our 2 projects includes fitting a differential equation and classifying wells using convolutional neural network. We will discuss the future of these at the end. We implemented our solution with PennyLane, TensorFlow, NVIDIA CUDA, cuQuantum, and Keras locally and also on a cloud. Hopefully, we could turn it into a paper. The goal of this is to reproduce the values of a function or image through the QML paradigm. We implemented a small single-qubit quantum circuit to fit a noisy sine dataset to great accuracy. However, we want to extend this to fit anything that follows a differentiable equation. This is a run from another paper describing the fitting of a differentiable equation and a related dampened sine function. The steps includes quantum support vector classifiers and quantum feature maps. Our capstone stack is to determine whether a weld is defective or not, and if defective, classify the 5 types of defects. The original dataset contains 25K grayscale chilling and 12K test images, all from frames from weld recordings. These are the 6 different types of classifications, and I have circled the sources of the defects, which will be the topic of our future. This is our machine learning overflow. Prepare using TensorFlow, downscale, trim. Apply the trainable adjustable Keras convolutional neural on the images. Apply classical dense layers of up to 32 to 256 channels on this reduced model. Refine the results, check the hyperparameters, and add or subtract or modify the layers using Keras. Classical results, we're only able to get like 30%. With the reduced model of 256 images. However, and this is a graph of that, we've ran the code on the cloud and we can get slightly better results of 40%. The quantum results perform significantly better, although it's more computationally complex. We got like 44% test accuracy, even with NVIDIA cuQuantum. We're not able to run the entire thing 100% epochs within the time limit. But these are the challenges. We need to revise our model, extend the model so it can also detect features that are specific to the defects, and recategorize them to skyrocket our test accuracy. The future of our project is we will scale the project and hopefully make it production grade that can also locate rather than decide the classification of this weld. Thank you for this presentation, and feel free to ask any questions for that.
Thank you, Mac. Wonderful. Next up, we have Q Frontier, Hanzay, and Mackinson Pulche.
Hello, everyone. My name is Haney, and our project is using quantum machine learning for conspicuous detection and production. And for this project task, we learned quantum computing through task 1, 2, and 3 using PennyLane. And for task 4, however, the main idea is about using quantum machine learning to learn a sine function, which we were able to do and achieve a perfect score of R square. And this success led us to adapt this model for task 5. And task 5 is the centerpiece of our project. Here we have 2 primary objectives. One is multi-class classification and binary classification. For multi-class, we implemented a QCNN to classify images into 6 different categories, as shown right here. And for binary classification, we developed a QCNN to classify images into 2 different categories. The methodology here is that we built a quantum circuit that employed amplitude, embedding, and quantum convolution layers, and then we measured the probability of the circuit to obtain the final state. And for multi-class classification result, as you can see here, the quantum model slightly outperformed the classical model in terms of accuracy and net loss. This suggests that the quantum model performs better in a complicated task compared to the classical methods. For binary classification, the classical model demonstrated a superior performance, achieving a higher accuracy. This again reinforces our idea that quantum models outperforms and excels in more complicated tasks rather than in simpler tasks. And as you can see here, we have the quantum versus classical results of the two models, so the two different classifiers. And in order to apply our model in real world, we took the initiative and built a prediction function combining both the binary classifier and the six class classification classifier. Essentially what this does is that it will take an image, classify it as either a good or a defective weld. If it's a defect, the multi-class classifier will kick in and then further classify that. And then for future scope, though, we would like to increase the number of qubits we're using and then explore various noise mitigation techniques. And of course, use higher resolution images to improve feature capture. And most importantly, though, we would like to develop a real-time classification system that is based on the prediction function that we have already built. This way, we will get feedback from the quality control line in real time. And of course, we would like to optimize our quantum circuit and hyperparameter tuning as well. And well, thank you very much for your time, and I hope you've enjoyed this presentation. Thank you.
Wonderful. Thanks a lot, Han.
Thank you.
And next up, we move on to this group Helios, Jia Young and Simon Lim. Please go ahead.
Hi, I'm Jiayang, and I'm presenting on behalf of Team Helios. We built a model that identifies faulty welds and their types by tackling the challenges in its parts. Firstly, we process the data by conducting EDA and using this info in our training. There's a big class imbalance in the dataset, thus we employed weighted sampling in our training. We also found that the dataset is made up of videos from different welding sessions composed of its frames. The imbalance is exacerbated in the videos. As the labels are given to videos as a whole, videos with some faulty welds would cause frames with good welds in that video to be labeled as faulty too, causing overfitting. Thus, we use an augmentation pipeline to improve the training dataset variety. The data is fed into our model, which is a hybrid convolutional neural network and ResNet 18. We use ResNet to extract features and use the QNN to refine them before using a dense layer for one-hot classification. We use the small ResNet model as larger models tended to overfit. We then pass the embeddings into the QNN, which we optimize to run in parallel during simulation using JAX. We then pass the embeddings into the QNN, which is initialized by multiplying each input feature with 3 trainable parameters to rotate each qubit. This is followed by repeated QNN layers that use rotations with trainable parameters and CNOT gates for entanglement. The output is the Z expectation of qubit 0. Finally, we use a dense classifier head. As we notice that each video shares the same output, we aggregate the results by using the most common output in that video as the label for all frames. Now onto our results. On the test set, we reach 85.7% accuracy with voting and 81.4% without, and 100% accuracy on whether a weld was faulty or not. Our confusion matrix shows generally good performance, but with difficulties for classes 4 and 5. Further training led to improvements in class 5, but at the expense of class 0, worsening overall results and suggesting that these classes may look similar. When using voting on a per video basis, we see improved performance. When classifying between good and faulty welds, our F1 scores are very high, achieving 100% accuracy when using voting. Through the loss and accuracy curves, we see that training more than 3 epochs causes overfitting. We performed ablation testing by removing ResNet. The QNN can learn independently, but is too small due to computational limitations when using simulations, leading to poor accuracy. Without the QNN, the ResNet is still able to perform quite well, which suggests that the QNN does not offer a big improvement, possibly due to its tiny size. To improve, we can reduce overfitting by improving the per frame labels or training on one video at a time instead. We can also use real quantum hardware to enlarge the quantum models beyond the limits of simulation. Further improvements to the model architecture for the QNN may take advantage of quantum properties better, improving performance. So with Team Helios, and thank you.
Beautiful. Thanks a lot. And we have another presentation from Dirac Dynamics, Asadullah bin Rahman. Please go ahead.
Hello everyone, I am Asadullah bin Rahman from my team Dirac Dynamics. This is the agenda of today's discussion, but before moving forward, I want to thank the Womanium Consortium for this wonderful bootcamp. And thanks for considering me as a finalist. So in task 4, the task was to implement a quantum machine learning model that reproduces the values of a sine function for interval 0 to 2 pi. So I generated 100 data points from the training from the sine function. 30% data were used for testing, and I shuffled the data. And I proposed two methods, a 1-layer and a 4-layer 1-qubit quantum regression model. To encode the data, I used angle embedding, and as answers, I chose a 1-layer and a 4-layer of rotation gates. And I also used gradient descent optimizer to optimize the cost function. So this is the prediction of 1-layer 1-qubit quantum regression model, and this is the output of 4-layer 1-qubit quantum regression model. This is the root mean square error, and mean absolute error between the two methods. And this is the cost function, cost comparison between the two methods. You can see the convergence is faster and lower for 4-layer model. Moving to task 3, the task was to implement a convolution neural network for MNIST digit classification. I chose 350 training data, 50 for validating the training process, and 100 data for final testing. And I chose proposed two models, a quantum classical hybrid CNN model and a classical CNN model. The hybrid CNN model, the quantum part has 3x3 kernel with stride 2. And as you can see, I have used 3x3 kernel. There are 9 elements, so I needed a 9-qubit system. So for answers, I used 4 strongly entangling layers with CZ as imperative. For the classical part, I used a convolutional 3x3 with a kernel with 32 channels, followed by a max pool of 2x2 kernel, dense layer, 64 dense nodes, and 10 classifying nodes. And to overcome the overfitting issue, I imposed a dropout of 50% in the middle. And the classical CNN is just the classical part of the hybrid CNN. This is my answers, and these are the output, 9 output channels. And these are the confusion matrix of hybrid channel, hybrid system, and the classical CNN model. These are the performance of the hybrid model and the classical model. The task 5 was to implement a convolutional neural network for conspicuity detection in production. I used 100 training data, 10 for validating the training process, and 50 for final testing. And from the 6 classes, I used only 2 classes. For the model is similar as that I used in task 3, the hybrid CNN model. And here I created a new quantum convolutional 2D. That is the output of the 9 output channels, and I converted it into a TensorFlow and wrapped the output into a TensorFlow and converted it into a TensorFlow layer. This is my hybrid model, and this is the confusion matrix of this model, and on the right hand side you can see the accuracy. So in future, I want to make more comprehensive analysis using the whole data set and to see how the model performs. I want to choose different embedding and different answers, and I want to choose the other classes as well. Thank you very much for your time. If you have any question, please feel free to ask.
Wonderful. Thanks a lot, Sahgal. And we move to the final presentation for the Fraunhofer project, and that is by Team Basket. Mustafa and Fatima Mahmood, please go ahead. We cannot hear you, Fatima.
Oh, apologies. Okay, my teammate is Mustafa, and we were working on quantum machine learning for conspicuity detection in production. We were trying to do binary classification on a real-world dataset, which is a TIG welding dataset using a quantum convolution neural network. We used the Python libraries Pennyline, scikit-learn, and PyTorch. So the circuit is designed. Has circle nearest neighbor connection. It has also 4 qubits. The 4 qubits has the quantum circuit has 2 layers, 1 convolutional layer and 1 pooling layer applied on all 4 qubits, and one convolution layer and one pooling applied on the first 2 qubits. So we measure the first qubit only and have the prediction through computing the expectation value of Pauli Z. So for the sign function approximation, the model was close to the actual sign function and with mean square error of 0.1. And for the TIG dataset, the model achieved 67% on the test dataset of accuracy, but we observed that because of the data imbalance, the model became biased by predicting only the bad welding, which is labeled by 1. So we considered undersampling the dominating class. Upon undersampling, we obtained 54% of accuracy on the test dataset. So the accuracy is not great, but the model is apparently learning and needs more improving. So we managed to implement a circuit of 4 qubits, QCNN circuit, and I used it on real world data, but the computational resource was the challenging part. And that moves us to the future outlook that we're looking forward to expand the dataset, use the whole dataset, look at the maybe try different convolutional pooling architecture, trying different data embedding, and looking forward to trying multi-class classification. Thank you.
Thank you. Wonderful. Thanks a lot, Fatima. We have the third and final presentation phase for today, that is the Classiq projects. So a little bit about Classiq. Classiq is a wonderful up-and-coming startup based out of Israel, but now also global in the United States as well. They have a pretty cool and a very efficient platform for all of you to use. And I'm very glad that many participants enjoyed doing different modules, listen to different lectures through the Classiq professionals. And now they get a chance to actually build projects using the same platform. The project was to try implementing some of the state-of-the-art algorithms and the papers which we have in the literature today, and try implementing on how you use the Classiq platform in implementing the same algorithms. So with that as the challenge description, we had a maximum team size of 3 persons. So different types of teams participated, and we had a lot of submissions. We have today selected the top 5 teams as the finalists. The first team, let's start with the presentation. Team Smooth Unitary Operators from Dimitrios and Hemant. Please go ahead, share your screen, and the stage is all yours.
Hello. So this is a project done in collaboration with Hemant. My name is Dimitrios Kranas. We chose the paper titled Exponential Quantum Speedup in Simulating Coupled Classical Oscillators. And to give you some context, we have a system of n-coupled harmonic oscillators. And with a clever redefinition of variables, we can convert this system to a system of particle spins, or qubits if you want, where the quantum state of the qubits in the amplitudes, we can encode the velocities and the displacement of the oscillators. Our goal is to use Classiq's platform to evolve that system and using a Hamiltonian simulation. Now, in particular, the tasks we achieved can be broken down in the following list of steps. We performed the initial state preparation. We constructed the effective Hamiltonian matrix. We decomposed this Hamiltonian matrix to a linear combination of Pauli unitaries. We did the block encoding. We ran the Hamiltonian simulation using the qubitization method. We explored the parameter space. Finally, at the end, we optimized for circuits width and depth parameters. And we studied what happens, how well is our code in different quantum hardware platforms. Now, during our development of the quantum algorithm, we faced major challenges that we had to overcome. The first one that we are particularly proud of was how to decompose a Hamiltonian matrix to a series of Pauli strings, of Pauli unitaries. And here is a screenshot from our code. This is the explanation of how we do it, and then we implement the code. But we managed to achieve to decompose an arbitrary n by n Hamiltonian matrix to a series of Pauli strings. Then we used high-level functions provided by Classiq to do the block encoding, but we still managed to address some points that they were not already taken care in the documentation. For example, how to do block encoding for Hamiltonians with decomposition coefficients that they are negative. So we managed to achieve that. And finally, we achieved the initial state preparation using two high-level functions from Classiq, prepare amplitude to encode the velocities and the displacements, followed by a unitary action to add the phases. Now, regarding the analysis, we first identify the critical ratio between masses and spring constants, above which our code becomes more efficient. Below that, roughly speaking, 10 to 2, 10 to 3 below this value, we're timing out. So this is a crucial number to keep in mind. Then we optimized our circuit for width and depth parameters, and here is our best values. And finally, we explored the performance of our quantum algorithm for different hardwares, and we found that there are some particular instances where our code can do much better. Now, future directions, we would like to study in greater detail the optimal model parameters and initial conditions that can further optimize the algorithm. We would like to do a more in-depth analysis of the depth and gate count versus the number of oscillators. We would like to compare these values with the complexity bounds, the theoretical complexity bounds from the paper. And finally, we would like to include dissipation and energy losses, an important thing for a realistic system. We have already started. We're looking forward to the future. And this week, we managed to produce some more results regarding the depth versus the scalability, the number of oscillators. And we would like to continue working on this line of thought. And with that, I would like to thank you very much for your attention.
Wonderful. Thanks a lot, Dimitrios. Amazing presentation. And we move on to the next team, that is Quantum Rookies, Veronica and Skibor. Are you there? Please go ahead.
Hi, hello everyone. We are Skibor and Veronica, and our project was Hamiltonian simulation using Classiq platform. We based this research on this paper from IBM. The model of choice is a 2D Ising model with this interaction term describing two spins talking magnetically to each other in an external magnetic field. The spins can only talk to the nearest neighbors on such a lattice, and our figure of choice is magnetization over time, how this quantity changes given this formula. The toy model is a 1D Ising model, which allows easy scalability and tests if our quantum simulations work at all. The time evolution is provided by Trotter-Suzuki decomposition, which in the Classiq platform implementation, a single step looks like this. The initial state of our model is ground states for all the qubits. The output is state after time t, and post-processing is just extracting magnetization from our data. Coming to the results of our test model, for 4 qubits, the exact evolution looks like this, the blue line. The classical implementation of Trotter-Suzuki decomposition is black dots, and in the red crosses, you see our quantum method. So all of them line up pretty nicely, which we already like. Moving forward to the enlarged model, so 9 qubits on a 2D plane, we perform resource estimation using Classiq methods. And what we can see is that the depth and number of 2-qubit gates scale linearly, showing that everything is already well optimized, while the width stays constant because we are not changing the number of qubits. What you can also use Classiq for is choosing the right model, the right hardware for your model. So from all the bunch of hardware we tested, we selected this IBM FES model as hardware, which provides the connectivity aligning with nearest neighbor interaction in the Ising model, and the following results for 25 qubits. For the future scope, first of all, we would like to dig into the IBM paper a bit more. So implement noisy hardware, which is not available in the Classiq simulator from the get-go, for instance, the polarizing Krauss gates. And second of all, when you have this running, you would like to actually be able to achieve noise amplification and zero noise extrapolation. And finally, run this on a real quantum hardware. Thank you very much.
Thank you. Wonderful. Next, we have with us Quantum Flux, Apurva, Kush, and Barnakon. Please go ahead.
Hi, everyone. I'm Apurva. I'll be presenting the work based on classically verifiable quantum advantage. Okay, sorry, my screen is somehow stuck. I'm sorry, I'll screen share again. Right. I'm so sorry for that. The paper talks about coming up with a protocol for finding a classically verifiable quantumness in any quantum prover. So for that, they come up with this trapdoor claw-free construction, which also uses Bell's inequality as the motivation. The one that we implemented was the Rebin's function, which is the function which is x square mod n. As for the task towards the project, we implemented the work, then we tried to generalize it and finally optimize it. As for generalization, we focused on trying to make sure that we could have the quantum algorithm calculate this x square mod n values for general n values, not just 2 to the power n type numbers. This is the overall protocol from the paper, where the verifier gives challenges to the prover. And if the prover manages to process and give the correct results, the verifier accepts it. If not, it gives another challenge and so on. The core step in that process was implementing this particular circuit that calculates the value of x square mod n in the Y register. We faced a lot of challenges in this particular portion. We finally solved it by using post-processing steps, and we saw that for numbers like n equal to 10, the measured values, the quantum measured values and the classical values were matching for all these x values. But if we change n to something else, for example, 15, there were some significant numbers where it was not matching, and the error is actually significant. This is still something that we would like to work on. Further, if the verifier goes to round 2 and 3 and gives the challenges to the prover, in that case, the probability of the verifier getting the correct result is based on this PCHSH, which, if it is coming out to be approximately 0.85, proves that the prover itself is a perfect quantum machine, meaning for us, it just meant that since we were using Classiq as the platform, it by default was a quantum device. But if it was to be used on a different device, a different simulator, this test would tell us whether what we're using is actual quantum device or not. Further, we did some resource estimation and found out that Azure Quantum is the one that gives the best depth and other parameters. So with this, we tried to optimize the depth of the circuit, and we found that we could reduce the depth a little bit from 268 to 255. For the future steps, we are interested in improving the algorithm itself by maybe having the QFT function itself dependent on the modulus value n, so that the periodicity is aligned accordingly. And another possibility that we can think of for future work is looking for applications of this work, maybe practical applications towards optimization, optimizing resource allocation, or even designing circuits. That's all. Thank you so much.
Thank you. Wonderful presentation, Apurva. Let's go ahead with Christina's presentation right now, and then we'll
Greetings, everyone. We, the Abstract Oscillators team, are delighted to present our project on developing novel quantum algorithms. Let's dive right in. Oh, okay. We work on implementing the quantum algorithm for solving classical coupled harmonic oscillators, which was developed theoretically in a recent 2023 paper by Babush and his collaborators. The harmonic oscillator is a fundamental model approximating many complex systems in nature with a potential energy minimum. For our case, we considered a spring mass system as shown in our slide. We utilized the Classiq platform for our quantum algorithm implementation. We began with a toy problem involving two masses connected by a spring. After encoding classical data, we prepared the Hamiltonian, evolved the quantum state, and obtained the final positions and velocities. We tested various Hamiltonian simulation techniques, including product-based and block encoding methods, and achieved good accuracy when benchmarked with classical solutions. Next, we applied our algorithm to a more complex system with 8 masses. We estimated the kinetic energy, which was an actual problem described in our paper. We also performed a resource estimation for the algorithm in terms of circuit depth, width, and 2-qubit gate counts on various IBM hardwares we used in our implementation. We chose IBM Osaka due to the lower synthesis time, and we tried to optimize our quantum program for width and depth. Unfortunately, we were not able to further optimize the program when using the Suzuki-Trotter methods. So we changed the evolution method to block encoding based qubitization method and continued using IBM Osaka for resource optimization. We were pleased to see that using Classiq's depth optimization technique and setting the maximum width to 127 qubits on IBM Osaka, we were able to reduce the circuit depth and 2-qubit gate count by nearly 40%. This is our qubitization method optimized circuit synthesized in Classiq. Next, we have a summary of our key achievements for each task. The main issues we encountered were global phase post-processing and size limitation. For the future, we aim to develop better post-processing techniques and apply the algorithm to real-world systems. We would like to acknowledge all the resources that were available to us for this project. With this, on behalf of my teammates, Kerem Yurtseven and Viraj de Souza, we would like to thank you for your attention and also Womanium for providing us with this opportunity. It was a great experience working together on this project. We welcome your comments, suggestions, and feedback. Thank you.
Thank you. A wonderful presentation. Thanks a lot, Christina. And we move to the final presentation for today. Team Cadets, over to you.
Good afternoon, everyone. My team's project was Evidence for the Utility of Quantum Computing Before Fault Tolerance by Yemen Oslan, me, Joseph Zuma, and Murshid. And so a big problem facing quantum computers to model many body systems is noise that's either inherent in these systems or comes from the outside environment. But before fault tolerance, we can still minimize noise to an extent. And to show this, my team has implemented a noise mitigation technique called zero noise extrapolation, or ZNE, in a trotterized time-evolved quantum circuit to simulate a 2D transverse field eigenmodel system. The figure you see right here is a diagram for the trotterized time step done by the original researchers in the paper we investigated. And so to start off, we implemented the Ising model Hamiltonian for a toy problem of 4 qubits. The apply Rx to all applies the Rx rotation gate to all qubits to simulate the influence of the global transverse field on all qubits. The ZZ layer is an RZZ layer that simulates the qubit-on-qubit interaction we get from maybe resonance or some other similar phenomenon. And so to implement that noise model, we first simulated noise with random polyrotation gates, and then we injected that into our C0 gates in order to describe an imperfect noisy control not gate. And so for our results, we ran with different qubit numbers. We mainly measured the expectation values for state 0, and we also ran the circuits multiple times with different noise functions, and so we can do ZNE more efficiently. And according to our results, and with the small samples we were able to execute with, the polynomial fitting performed better than the exponential fitting, with the polynomial fitting having an percent error of 3.12% for our most promising data point. And going forward, in understanding how noise works in these many-body systems, we can implement the noise mitigation techniques for different hardware architectures, because we use the same architecture as the original researchers did. we could run the algorithm with a higher number of qubits in samples because we used 16 maximum instead of 64 or 32. And then we could also try different types of noise. And so instead of random stochastic noise, we could do photons hitting individual qubits in certain parts of the device in order to simulate, for example, light radiation interacting with our system. And these are references. And thank you very much.
Things are about to change. After months of lectures, lessons, assignments, finding your team members, identifying the project, working on the project, all those hours of coding, decoding, troubleshooting, debugging, making the presentation, and coming and delivering it today. This is a chance for you. This is your time. Over to you, Vardaan.
Okay, yeah, let's get started. First of all, congratulations, everyone. And over we move to the award ceremony. First up, we have the grant winner for the Technical Merit Prize for the Quantum Plus AI for Climate Challenge. Next slide, please. And Marlo, do you want to announce the winners?
Please go ahead. I will do the fellows. Wonderful.
Okay, so it's Team Q Mars. Congratulations, everyone. Congratulations, Rishikesh, Abdullah, Sarah, Mahem. Amazing presentation. You stood out from all the other finalists. You are now the lucky winners of the grant from Womanium for the technical merit winner for AI plus quantum for climate project. Congratulations, everyone, once again. Feel free to take a screenshot and post it on LinkedIn and on your Discord servers as well. Please spam all the social media channels. You all deserve it.
Yeah, and we will be obviously sharing certificates and other things at the end of this as well. But great job. I think we had a really tough time here as well. There was a lot of creative approaches to NNL. So great job again. We thought this was really stood out.
And everybody stick around till the end because we would love to talk to all of you. And yes, Abdullah, good to see you.
All right, next up we have.
Yeah, next up we have the Womanium grant winner for technical merit winner for the second project we had with Fraunhofer for QML for conspicuity detection. And the winner is, we could have a drum roll over here,
Yes.
Quantomics, Team Quantomics. So Hao, Mac, Yang Li, congratulations. Mohammad Reza Kadaho, congratulations. Amazing work once again. And both of you, congratulations. And yeah.
Yeah. We also had another, the duo team. I think, they were really fantastic, really tight. I think with all of you, we want to talk about fellowship opportunities as well. So stick around, but dynamic duo, right, Vardaan?
Yes.
Exactly. Yes.
There was a very close competition between the other team that was the dynamic duo. So I think that was Chris. Yeah, I think that was Hussein and another team member. I'm sorry for getting the name, but yeah, that team was excellent as well.
Yes. All right, and the third one. This is a project with Classiq. We have two winners again.
Yeah, and the winners we have for the technical merit winner for grants is Abstract Oscillators. Congratulations, Viraj, Daniel D'Souza, Karam Hirsovan, and Christina Redian. You guys deserve it. Excellent presentation, excellent work. And not just the presentation, we also had a look at your module work. So you did all the homeworks, you completed all the assignments, you were consistent throughout the entire program. So a huge shout out to all three of them for continuously working on the Classiq platform, improving your skills. Amazing work.
Yeah, that's true. All right, yeah, so now we have some more grant winners. This is focused on two other prizes which we had put on GitHub, which is best presentation. It's something that I think it's really important in life is how do you present. I think all of you did an amazing job. Most of you stuck to 3 minutes. You presented well. You were very clear. I never heard any filler words. But again, this is just a really good skill to have is how do you present well and how do you make a story come alive. And this is especially true for science. I remember actually going to a lot of scientific conferences throughout my life, and it's always been like dull, and there's never been a thinking of like, well, how does this change? How do you do things in a way that's different? And one of the people that that I've always looked up to is Dr. Aarti Prabhakar. Dr. Aarti, she led NIST, which is the National Institute of Science and Technology, at the age of 34. She then became the head of DARPA, again at a very young age. And today she's at the White House Office of Science Technology Policy. And when she looks at a presentation, she always asks, what is the difference you've made that, in this case, that the climate will notice, or in other cases that a whole industry will notice? And that's where, your power of a story becomes really important. So I was really impressed with Quantumaniacs. I think you guys did a really good job. Why is crop detection important? Putting that into context, and how do we use science to facilitate better crop detection and agriculture and feeding the world. So really great job. Khadija, we thought your presentation was really well done as well. So good job there. I still, of course, love the tornado with the scary eyes and all the other creative stuff you guys did. But a really good job, Khadija. All right. And then the next one, sorry, Raj, over to you, startup potential. Yeah.
It was very difficult to pick just one because it is about the potential. And I found that many of you have tremendous potential once you have been nurtured properly and once you identify your purpose and direction. So we identified a couple of teams because we feel that you have potential. Of course, it is one thing to have potential, but it is another thing to build it, develop it, and take it further. So for the startup potential, these are the teams that we were able to identify.
Yeah.
1, Entangled Energy. 2, Q-Earth, Quantumaniacs, and Helios. And all of you should get in touch with us because we want to actually work with you to identify what your interests are and identify the purpose and the potential and to realize it. Over to you, Prachi.
Yeah, I think you all phrased it as a potential next step here. Entangled Energy, Maria, your presentation was really good. Your team did a great job. It's a really high interest field, material science, and using quantum AI for it. Yeah, so let's pursue and talk further, right? Because I think there's a lot of research going on in this field using traditional AI, and how you use quantum for material science. Yeah, very, very good question. And this can again revolutionize things. You're looking at it from a photovoltaic perspective. I think literally every other chemical in the world can be changed if we perhaps use quantum and AI in promising ways. So great job. Same with Quantumaniacs. I think there's a really good application side there, so we want to support you. Q-Earth as well. I think there's a whole app idea there, Mahmoud. So let's discuss. And Helios, you also had a great presentation. We really love that. So good job. It was nice and colorful. And again, we are curious to see where you would like to take this to the next step, and we are happy to mentor you based on again who is willing to take things forward.
Yes,
All
indeed.
right.
Speaking
Yes.
of next steps, these are just your starting steps. Of course, for a startup, these are your starting steps. So this is you on your journey today. Happy, but a long way to go. And our goal is to make sure that you reach there so that you become the king, you become the winner. So get in touch with us because there is a lot more to be done and a lot more places to go until you can win the crown. And my job here is to make sure that you become the winner. So get in touch.
All right. And now we have a bunch of other prizes we want to give. Exactly. I like that spirit, Yara. Vardaan, over to you.
Okay, yeah, so next up, we will start announcing the QSL fellowships. So a little bit of background on what QSL fellowships would be like. You would be nominated today. That means all the names you would be announcing, they are not team names, rather they are individual nominations. And all those who are nominated will receive follow-up mails from us to decide the next steps. And the next steps would ideally be a one-on-one interview with you to understand your future goals, your availability, and how you would like to work on the projects. But these nominations are a good step forward. Some of the nominations will ultimately get converted into selections. So let's say you have 5 nominations. Out of those 5, let's say 2 or 3 will be finally getting selected for the fellowships. And what do these fellowships mean? You would be working with our partners, the Naval Nuclear Lab, Fraunhofer Institute, and Classiq, starting from September 1st, so just next month. And those are very exciting fellowship opportunities. You get to work with some of the best researchers, you get to work on a real world problem, and you get a stipend to work on it. So it's kind of a win-win situation for all of you over there. So let's begin with the fellowship nominations. And I would like to hand it over to Marlu to go ahead with it.
Yes. And please go back one slide before we show the results already. Great. First of all, the deliberation was very hard. I will share some feedback from Classiq. Classiq was impressed by the quality of what the participants showed. It was truly exceptional. We're blown away by the first and then by all the others after that. So we are happy that we can not only give fellowships, but also grants to really do justice to the great achievements that you did. We selected 8 nominees for the fellowships that will be interviewed the upcoming days for 3 fellowship positions. And the first fellowship nominee is Veronica Golets from a truly exceptional team with some of the highest scores in the project. The second fellowship nominee is Hemant Velmurugan. Congratulations to you. The third fellowship nominee is Dimitrios Kranas. And now we will speed up. Please continue. Yaman Goslan. Next, Christina Radian. Apurva Dingra. Kiram Yurtseven. Viraj Daniel Souza. And those were the 8 fellows nominated for the Classiq fellowships. Eden is here and would like to share some feedback on all the great work you did. Eden, if you're still there, please unmute.
Yeah. Hi, everyone. So it was really a pleasure to work with you throughout the project. So from the sessions that we had together, the office hours, the homework, viewing the homework assignments, it was really a great work. And today's and the final, all the final projects that we reviewed, both in today's presentation, but also through your submission via GitHub. It was really, really high quality, even more than we expected. And we are really looking forward to continue work with the fellows, but in general with the entire community. Also, we are really encourage you to take the projects that you did one step further and to contribute to the open source community. So either via our GitHub repository to share the solutions that you had. I think it really can promote the community as a general, focusing on implementation of advanced quantum algorithms, and also via the general community, so also via other platforms, because you really did a great job and that can promote the community as a whole. So very well done to all of you.
A big applause to everyone. And all the 5 finalist projects presented here have scored extremely high, all with a score between 8 and 10 out of 10. A big applause. You can be extremely proud of doing this actually very difficult project so well. Applause to everyone. Congratulations. And we look forward to the phase 2 of this project in the actual QSL project with 3 of the participants just presented here. Thank you, Eden. Thank you, Classiq team. And that brings us to the next project, the Naval Nuclear Lab project. Yes, and please stay on this slide. Indeed, we also have Brian here to share some feedback, and we were also extremely impressed by these projects. Not only the methodology, the coding, but also the creativity, the novelty, coming up with many ideas, looking for into some parts that hadn't been done yet, and others that is a really hot topic now, and you managed to identify that and go about it in your way. So I am going to mention the 5 QSL fellowship nominees that were selected. And I must say that here there was a requirement for US citizenship. And that means that other people who were truly exceptional and that we would love to give a shout out to separately later won't be in this list because of the citizenship, but you did amazing work and we are extremely proud of you and we look forward to staying in touch. The first QSL fellowship nominee for NNL is Nidia Asaf Aragon. Congratulations. fantastic work, fantastic presentation, and very novel. We look forward to keeping working on this project. Second, Maham Khalid. Fantastic project. We are extremely impressed. Third, Maria Nikos Alan Pasaro. Also a wonderful project that truly also resonates with NNL's goals. Very in-depth, showing so many techniques and methodology, and great presentation. Next QSL Fellowship nominee, Shreya Das. Also mentioned for exceptional presentation, very impressed by the work, and in this program we have people of all ages, and age shouldn't play a role for science, but we want to mention that we are extremely impressed that you did this at an age of 16 years old. So fantastic. Next fellowship nominee is Samiha Rahman. Fantastic work, and we really look forward to interviewing you for the QSL fellowship and working with you. And is this 5 yet? I think so, otherwise we would click forward. Brian is here to share some general feedback and assessment of what he has seen.
Thanks, Marlo. Thanks, everybody. And congratulations to all the winners. It was very difficult trying to pick a winner out of all the finalists I reviewed. Lots of creative ideas, lots of very thorough methodologies for what was a very, admittedly very challenging research project to do in only 6 weeks. And so I was also pleased to see that everybody managed to get a code implementation done. I had a chance to try a few of them, and it was very impressive. Some made full featured apps out of it. Some focused more on the analysis. But they're all very great, and I encourage you to continue learning more about how to do research. And if this is your first time, great job. And if you're experienced, keep it up.
Fantastic. Congratulations to all the nominees, and really to all nominees here, fantastic work. To all teammates, fantastic work, and truly everyone who presented. We were very impressed, and it was very hard to pick. Then the third QSL project will be with Fraunhofer ITWM, and we have selected eight nominees that will be interviewed the upcoming days. Please skip forward to the first nominee. The first nominee is Martina Anna Tsuba. Martina was part of the detection duo, and all of the projects that will be mentioned now were extremely good, but this project was highest rated, and the judges were really extremely impressed by your work. The next QSL Fellowship nominee is Jose Antonio Contreras Ortiz. Congratulations, and I will speed up again because of time. The third nominee is Hussein Shiri. Fantastic work, and part of this team that performed the very best, although everyone here was really amazing. The fourth nominee, Ricardo Rioda Santiago Sanchez. Congratulations. Fantastic. The fifth nominee, Mackensen Polche. Congratulations. And the sixth, Asadullah bin Rahman. Congratulations. The upcoming days you will be interviewed. And the next, Mohammad Reza Korazu Masule. Wonderful work. Congratulations. Hein Zai Yaro. Very engaged. Congratulations. You will be interviewed the next days. Hao Mak Yang Lei. And we haven't indicated the teams here, but we will share the scores with you because all of these projects, you did amazing work, and we are extremely excited. And that was it for the QSL Fellowship nominees for Fraunhofer ITWM. Vardaan will follow up with you about the next steps, but it is not all, because more people really stood out, whether it was the engagement on the Discord, the help with everyone, whether it was on a technical or organizational level, or bringing some fun into the group. And we would like to acknowledge that as well.
Yeah, I think with the Womanium programs, you always try to have a heart and soul. We are not only here to train you in the most advanced scientific domains, but we're also here to build a global community, to help each other, to learn from each other, and be inspired from each other. So we're really grateful to everybody who made this into a warm, happy, and a community you can go to and ask a question. And you could do that at a university and maybe find a professor in a week, or you could come to the Discord channel, and within minutes, your questions will be answered. And this is the power that I think, all of us, we've really created a kind of spirit and magic. And, Jasmine, who is also our soul within the Womanium program on Discord, I'm very happy she selected a few of you for really these special mentions. Go ahead, Jasmine.
Okay. Yes, we do have a few outstanding people that we wanted to mention. And very first on that list, you know that this summer we have elected some mentors / Jasminians, and we wanted to highlight Hussein and Nagar for all of the hard work they've done as mentors this summer. Truly, both of you, thank you so much. I always see you guys around the server helping people with various questions, and especially the technical difficulties, which is even a step beyond what I can resolve. So truly, thank you both so much for always being available and always looking out for the people in this server. I know there's many people here, I think, who could appreciate the help that you've given this summer. So congrats to Hussein and Nagar. For meme creation, we all saw it coming. We all knew it. If you've been in the Discord at all today, you know who it is. It's Parsa. Parsa has given us not only some of the best memes, but the quickest memes in the Womanium West. We know not how, we know not why, but he has provided every single time. So for always bringing the laughs as expeditiously and creatively as possible. Yes, Farsa, it is you. And this is the peak activity. For media content, we have Sujit. Thank you so much, Sujit. We've watched your posts across LinkedIn and also your various Medium articles. They're always so well articulated, and we really appreciate just you getting to celebrate your achievements and what you've done this summer and the love you have for the program. Couldn't be more glad to see that there are people who enjoy it so much that they just feel the need to use their gift in writing to express it. So for media content creator, we highlight Sujit. Hooray! And our next one goes to our high school highlight, where we have highlighted Kasani Pine. Kasani, you've seen your grades, you've been doing really well in this program, even as a high school student. Similarly, we loved seeing your LinkedIn post from earlier this summer about your experience with the program and what you've learned in these modules, and your overall activity in the server. We are just so proud to see the young high school talent really doing amazing in this program and learning as they go. And we wanted to honor that with a special shout out to you, Kasani. So hooray! Oh boy. And I think we have our next one goes to for Discord Server Spirit Award, Vaniza, because someone has to try to keep this Discord alive. It is the community, the heart, the soul that makes Womanium what it is, and that pulse exists within the Discord server. And for trying to get a general fun chat going, and for always reminding us that we were not engaging enough with it. We highlight Faniza for our Discord Server Spirit Award this summer. So I'll probably pester her later about it. So hooray! And that's all for our Discord Server Highlight Awards. Thank you all for making this program and the community what it is at Womanium.
So you must be wondering what's our next steps.
Right. So first of all, congratulations, everyone. The next step in general for all the award winners, all the grant winners, all the fellowship nominees would be the Womanium team reaching out to you via mail. So just make sure that the Womanium mail ID is not in the spam folder. It's clearly marked to land in your inbox, and you should be hearing back from us in about a week's time. For specific next steps from the grant winners, I think the Womanium team will reach out to you, coordinate the next steps, how you want to receive the grant monetary stipend, what are your next goals, really guide you in your next steps. If you want to create a YouTube channel, what is the best way moving forward? If you want to attend a conference or publish a publication, you want hardware credits with that grant money, whatever you want, right? We will make sure that you have the right guidance and the mentorship to take you forward. And obviously, we'll discuss how to wire you the stipends and the money. Talking about the QSL Fellowship nominees, so like I mentioned, this is the nomination stage. So congratulations, everyone who has been nominated. Over the next few days, we will be conducting one-to-one interviews with all the nominations. Again, make sure that you check your inboxes. You should be receiving a mail from us in the next 2 days itself. And keep your schedules a little bit flexible from August 17th to August 19th. That is when we'll try to cover maximum interviews. You should receive a Calendly link from our side where you can schedule your interviews and go ahead with it. Please make sure that only one interview per person would be conducted because of the time and because we have a lot of nominations to just keep everything in control and on track. Make sure that you do attend your interviews whenever you book it on a Calendly link. And yeah, so looking forward to talking to all the nominees and taking it further from there. Also keep in mind that the final fellowships, fellows who are getting selected for the fellowships will be starting the project by September 1. So they should be aware that starting September 1, 3 months is the timeline for the project. They should have certain availability over there. These would be part-time projects and remote projects. You can work from your home and work alongside your studies, alongside your current jobs. It's all okay. We are very flexible on that. But the rough date, which you can keep in mind, is first week of September. That is when the projects will get started. And to everyone else, yeah, we will definitely reach out to you very soon. So keep an eye on your mailboxes. And that is it. If there are any questions, Discord is the way to go. You can always reach out to us, tag the Womanium team, tag any one of us on Discord, and we'll be very happy to respond over there. If there are still any questions, and in case we do miss out on Discord messages, you can also mail us, quantum@womanium.org, and you can tag me or Jasmine along with it, and we'll make sure that your queries get responded as fast as possible. So with this, I think we come to conclusion. Thanks a lot for the entire Womanium team. Me and Marlu are the faces you have been seeing, but there's a lot going on in the background. So thanks a lot, Prachi, Raj, Haiza, Alex, Marilena for covering up in the back end. Akshita, Miriam, Ananya, Lindsay, thank you all very much for volunteering your time and making sure that the program, entire program, right, from 2 months onwards, but also before that, there was a lot of stuff going on in the back end, making sure that the speakers are confirmed, making sure that the schedule is all good, trying to get the best lab tours possible, making sure that the partnerships we do are with the best of the best companies out there so that all of you can have a good program to learn from. So once again, thank you everyone for their contributions. And finally, a very warm thanks to all the QSL team members, Jasmine, Bakao, Horia, thank you all. You have been excellent. I love working with all of you, and to all the fellows who have been nominated, you would be working with us very soon. So yeah, I'm really eager to work with all of you and have a great time together. Thank you once again.